As we have seen, standard scientific realism has various problems. This has led to attempts to limit the scope of realism. Perhaps we can grant that we should be sceptical of substantial parts of science, while still being realist about other parts. In the last video, we examined Hacking's entity realism, which attempts to limit realism only to those entities that we can manipulate. However, probably the most popular option for limiting realism is structural realism. This has a long history. It was held by many philosophers in the late 19th and early 20th centuries, but it was then forgotten for many decades. It was revived in the 80s by the philosopher John Worrall. Worrall suggests that structural realism offers the best of both worlds. He explicitly intends structural realism to answer both the no miracles argument and the pessimistic induction argument. As you should recall from earlier videos, no miracles is the argument that scientific realism is the best or only explanation for the stunning predictive and technological success of science. The pessimistic induction, on the other hand, tries to undermine realism by noting that most of the theories that were once widely accepted have subsequently been shown to be false. Worrall thinks that both of these arguments are very powerful. Of course, the problem is that they pull in opposite directions. He thinks that structural realism is the answer. Structural realism is essentially the opposite of entity realism. It holds that we should be sceptical of entities like electrons, photons, mitochondria, black holes, and so on, but that we should be realist about the theoretical or mathematical structure that is postulated by theories. Let me review the example I gave in the introductory video. I think it's a good example, and it's been a little while since that video, so it might be worth reviewing it. Here is a diagram showing the behaviour of light. This shows what happens when light travels from one medium into another. Here the first medium is at the bottom and the second medium is at the top. The incident beam is the light coming through the first medium towards the second medium. This beam here shows the light reflected from the surface of the second medium, and this refracted ray is the light that travels through the second medium. There is a very simple law for reflection. The angle of incidence equals the angle of reflection, assuming the surface is smooth. The angle that the light comes in at is equal to the angle it's reflected. Now the angle of refraction, for this refracted ray here, the angle of refraction depends on the medium through which the light travels. It's a bit more complicated, but it's given by Snell's law, which says that the refractive index, labelled N1, of the first medium times the sine of the angle of incidence, or I, is equal to the refractive index, or N2, of the second medium times the sine of the angle of refraction, or R. So if we know the refractive index of the first and the second medium, and we know the angle of incidence of the first medium, we can work out the angle of refraction. Snell's law can also be expressed in terms of velocity. The light has a certain velocity, v1, in the first medium, and a different velocity, v2, through the second. v1 over the sine of the angle of incidence is equal to v2 over the sine of the angle of refraction. You can look up Snell's law if you want more of an explanation. So that the point for us is scientists have developed equations that describe the behaviour of light. These equations were well known during the 1800s when ether theory was popular. Remember that according to the ether theory, light is a wave and it propagates through a very subtle universal substance called the ether. Light is waves in the ether. When the ether theory was displaced and it became accepted that light is composed of photons, these rather bizarre entities that have both wave and particle properties, these laws were retained. The mathematical description of the behaviour of light survived the elimination of the ether. The behaviour of photons obeys laws that are very similar on a formal level to laws describing the behaviour of waves in the ether. So this is the sort of thing we mean by structure. And Worrall suggests that over the history of science, theoretical claims concerning entities are displaced, but theoretical claims concerning structure are retained. So as I noted, Worrall argues that structural realism is the best of both worlds. It answers both the no miracles argument and the pessimistic induction. First, since structural realism holds that we discover facts about the underlying structure of the world, it explains the success of science in the same way the realist does. Scientific theories are successful because they are true in an important respect. But because this view counters scepticism about the entities postulated by scientific theories, it also answers the pessimistic induction. Maybe we are completely wrong about the nature of electrons and photons and quarks, still we should accept the underlying laws in which these entities figure. Of course, this argument for structural realism is only as good as the no miracles argument and the pessimistic induction are. As we saw, both of these arguments have some serious problems. But there are other motivations for structural realism, one of which I will discuss a little later. Still, it should be clear that the view has some intuitive force. Let's consider some problems. First of all, what exactly is structure? I've given an intuitive example of what the structural realist is talking about, but we really need to specify more precisely what is meant by this term. One suggestion for defining structure was given by Bertrand Russell, who was he wasn't really a structural realist, but he held something kind of similar in some ways. But he defined structure, and the structural realist might adopt Russell's definition. Here's how Russell defines structure. I quote, "We shall say that a class alpha ordered by the relation R has the same structure as a class beta ordered by the relation S if to every term in alpha some one term in beta corresponds, and vice versa, and if when two terms in alpha have the relation R, then the corresponding terms in beta have the relation S, and vice versa." That's quite abstract, so here's an illustration from Anjan Chakravarti. Consider a collection of 10 cakes of different masses. The cakes can be ordered by the relation heavier than. One cake is heavier than another. Now consider a collection of 10 spoons of different lengths. These can be ordered by the relation longer than. We can say one spoon is longer than another. These two collections have the same structure on Russell's view. You can see that to each cake, we can say that a spoon corresponds, and to each spoon a cake corresponds, because there's 10 cakes and 10 spoons. And we might say that the lightest cake corresponds to the shortest spoon. Furthermore, the relation heavier than, the relation between the cakes, corresponds to the relation longer than, which holds between the spoons. Cake 1 is heavier than cake 2. Spoon 1 is longer than spoon 2. Of course, one could also relate them in other ways. We could say that the lightest cake corresponds to the longest spoon, in which case the relation heavier than will correspond to the relation shorter than, so that the correspondence will be flipped. The point is just that there's a sense here in which these two collections share an abstract structure. And the important thing to note is that the members of these two classes may be completely different kinds of things. The relations between them may be completely different kinds of relations. Cakes are nothing like spoons. The point is simply that we can relate each cake to each spoon, where for two cakes such that one is heavier than another, there are two spoons such that one is longer than another. So this might be what the structural realist has in mind. Unfortunately, Russell's definition of structure is met with a serious objection from Max Newman, which has come to be known as Newman's problem, or Newman's objection. Newman says, and I quote, "Any collection of things can be organised so as to have the structure W, where W is an arbitrary structure, provided there are the right number of them. Hence the doctrine that only structure is known involves the doctrine that nothing can be known that is not logically deducible from the mere fact of existence, except the number of constituting objects." Basically, Newman's objection is that provided we have the right number of entities, we can order those entities into any structure we like, given Russell's definition of structure. Now, Newman's argument for this is somewhat technical, but the essential point to note is that we can always put any objects we like into ordered pairs. An ordered pair is just a mathematical construct. Suppose we have two objects A and B, then the ordered pair AB is different from the ordered pair BA. Of course, there are also unordered pairs, such that the pair AB and the pair BA are identical, but the ordered pair is all we're saying is that AB is different from the other ordered pair BA. This is, again, it's just a mathematical operation. We can perform this operation on anything. Just take two objects on your table, let's say my computer and my phone. Well, I can put my computer and my phone in an ordered pair, computer, phone. Objects in an ordered pair do not have to have anything in common. Okay, so suppose we have 10 objects, A, B, C, D, E, and so on. Then we can put them into ordered pairs, A, B, B, C, C, D, etc. Again, this is just a mathematical operation. It doesn't matter what the 10 objects are or what their properties are. We can simply stipulate that we're treating them as ordered pairs. But now notice that by Russell's criterion, this set of 10 objects will have the same structure as our 10 cakes ordered by the heavier than relation. Because all this relation comes out to is that what we're saying is cake 1 is heavier than cake 2, cake 2 is heavier than cake 3, and so on. When we abstract away from the entities and we abstract away from the relations, we just end up with a structure like this, A, B, B, C, and so on. Okay, if we replace cake 1 with A and cake 2 with B, and we abstract away from the relation, then we just get a pair, A, B. That's it. And so the cakes end up having the same structure as our 10 random objects. Basically, the point is that for any 10 objects, we can put them into any ordered pairs we like. So any set of 10 objects will all have the same structures, and there are a large variety of structures they will have. So how might the structural realist respond? Well, one obvious response is to distinguish between trivial and important relations. The worry about the Newman objection is that, well, I mean, sure, we can define ordered pairs however we wish, but this is just a kind of mathematical trick. If we take 10 random objects, let's say computer, phone, kitchen knife, the Andromeda galaxy, an electron, a mitochondrion, an ocean, a mountain, a house, and a car. Well, yes, we can place these objects into ordered pairs, so we might have the ordered pair electron, kitchen knife. That's fine, but in what sense does a relation hold between an electron and a kitchen knife, merely in virtue of us stipulating this ordered pair? I mean, that's a completely trivial kind of relation. On the other hand, when we look at cakes, the relation heavier than actually tracks something important. The relation that we've defined between the electron and the kitchen knife is a mathematical construction, whereas the heavier than relation is an objective feature of the world. I think that there are two problems with this response. First, and I think most importantly, the judgment about which relations are trivial and which are important depends on more than just knowledge of structure. I mean, really, it's precisely the point of Newman's objection, that from the structure alone, we can't make the distinction between trivial and important relations, because the structure alone is the same for both. We can say that the relation defined by the ordered pair electron-kitchen knife is trivial, whereas the relation expressed with cake 1 is heavier than cake 2, that's an important relation. We can say that only because we can specify the entities in the relation. If we had no knowledge beyond the structure, then in each case we would just have an abstract ordered pair AB, like that up there. That's all we would have in each case. So that doesn't really seem to solve the problem, because we need to know more than structure in order to know that a relation is trivial or important. In any case, notice that even if the distinction between trivial and important relations is defensible, there will probably be all sorts of important relations corresponding to all the possible ordered pairs. Consider, for example, the number of carbon-12 isotopes in the cakes. That's clearly an objective feature of the world. We can order cakes by how they differ in their number of carbon-12 isotopes. We might get one order from that. Similarly, we can order cakes by their time of birth. We might get a different order. We can order cakes by their height. We get a different order. We can order them by their chocolate content, and so on. Even if we focus on purportedly important relations, even if we focus on relations that are objective features of the world, we will probably be able to find these objective important relations that allow us to order cakes in whatever way we wish. So again, it's really not clear that Russell's definition of structure is particularly persuasive. So we might then want to look for a different way to define structure. A second option is to define structure directly in terms of relations. In our example of Russell's definition of structure, the relation heavier than in cakes is taken to correspond to the relation longer than between spoons, so that the 10 cakes and the 10 spoons can be said to have the same structure. Maybe this is too abstract. Perhaps instead we can just look at the relations themselves as defining structure. So the structure of the cakes is A is heavier than B, B is heavier than C, C is heavier than D. We've abstracted away from the entities, but left the relations between the entities. In this case, the longer than relation gives a different structure. So the 10 spoons will only have the same structure if they all have different masses. On this view, then, science doesn't give us knowledge of entities, but it does give us direct knowledge of the relations between entities. So this, on this definition of structure, structure certainly tells us something interesting. Knowledge of structure is not trivial. The main problem is that it arguably ends up entailing realism about entities as well. If we know that one entity is heavier than another, we must know that there are entities that have different masses, and we must know something about their respective masses. Evidently, the more relations we know, the more we know about the entities. If structure is defined in terms of the relations themselves, then the more that science teaches us about the structure of the unobservable, the more we will know about unobservable entities. So I guess ultimately the challenge for the structural realist is that she needs to define structure in such a way that it doesn't become trivialized, as Russell's definition did, but also such that it doesn't end up entailing knowledge of entities as well. And that's a very difficult line to tread. A second objection is that structural realism simply isn't restrictive enough, because pretty much anything can be said to have a structure, so structure is also lost in theory change. For instance, regarding the example of the equations describing the behaviour of light, Anjan Chakravarti points out that scientists also developed many mathematical equations describing the mechanics of the ether. When the ether theory was displaced, these equations were of course shown to be false. There is no ether, so there is no structure to capture there. In general, the problem here is that anything can be described mathematically. So entities entail mathematical structure. In other words, if we have a theory that postulates certain entities, we can say various things about the structure of those entities. And that means that when the entities are displaced, structure is displaced as well. So it's not really clear how restricting realism to structure is supposed to help answer the pessimistic induction about theory change. The primary response to this is that structural realism has to be limited to particular kinds of structures. We can distinguish equations that are necessary for the theory to deliver the right predictions from equations that simply describe objects postulated by the theory. In the example of light, equations such as Snell's law were necessary for the theory to square with our observations. On the other hand, equations that focused only on describing the ether made very little, if any, contribution to the predictive accuracy of the theories of light. So the structural realist will need to distinguish those aspects of theories that are sort of purely structural from those aspects that are also structural but are derivative on entities. And the structural realist will then say that structural claims that are derivative on entities are not to be believed. Again, this is a very fine line. That's a very difficult task to make that line clear. I mean, one obvious problem is that in many cases it just doesn't seem to be the case that the structure derivative on entities plays no part in prediction. Consider, for instance, theories of stellar structure and evolution. We can describe the interiors of stars, how stars develop and die and so on. We can describe all of that mathematically. Here's a diagram, simple diagram showing the projected interior of the sun. So that we can clearly kind of capture this in mathematical terms, but I mean, we're obviously describing an entity here, and the predictive success of theories of stellar composition clearly depend on claims about entities. And it's also evident that if the theories of stellar structure and stellar evolution were to change, then obviously this description of the sun's structure will be displaced as well. So it's really not clear that we can separate different kinds of structural claims in the way that the structural realist will need to do. A third objection is that structural realism has a kind of physics bias. There's a famous paper by the physicist Eugene Wigner called "The Unreasonable Effectiveness of Mathematics in Natural Science," which is concerned with how powerful mathematics has been in science. Science seems to be largely mathematical. Mathematics is really a very useful tool. Much of what you learn when you open a science textbook will be equations and mathematical models and mathematical structures. But as many responses to the paper pointed out, what Wigner was really talking about was not science but physics. When we look at other sciences, if you look at biology, paleontology, psychology, geology and so on, you find less mathematics, and where mathematics is used, it's often less effective. So the worry is that structural realism is perhaps plausible for physics, but when we look at other sciences, there's less mathematics, and so the structural realist approach is going to be less plausible there. The primary response to this problem is that structure does not necessarily have to be strictly mathematical. Harold Kincaid has defended the application of structural realism to the social sciences. And I mean, social sciences are about as different from physics as a science could get. According to Kincaid, social scientists often explain social phenomena in terms of social structure, where social structure, to quote Kincaid, consists in a relation not between individuals but between positions or statuses and roles. Kincaid continues, he says, "A position or a status is a socially designated category into which individuals or groups fall. Obvious examples are producers and consumers, the elements of the organisational chart of an institution, and social groupings such as ethnic groups, economic elites, and so on. Roles are descriptions of traits and behaviours associated with the position." So we have social categories, these are the positions, with certain traits and behaviours associated with these categories. We can consider the behaviours of producers and consumers, for example. Social structure consists in the relations between the categories and the traits and behaviours associated with those categories. The crucial point to note is that in these analyses, individuals don't really matter. We can explain a certain social phenomenon in terms of the positions and the roles abstractly defined. An individual person who occupies a certain position, who plays a certain role, that individual will have various characteristics as an individual. They'll have a gender, an age, a certain personality, and so on. But when we analyse social structure, we can abstract away from all of these features. If we're talking about producers and consumers, for example, we can ignore most of the features of individual producers and individual consumers. It's this ability to abstract away from individual traits. This is what allows us to identify broad repeating patterns in social phenomena across many different times and places. The broader patterns can remain the same even if very different kinds of individuals occupy the relevant positions and roles. So maybe this is an example of how sciences other than physics can appeal to structure. Kincaid thinks that structural realism is actually quite a plausible account of what's going on in the social sciences. Right, well, so far we've been talking about structural realism in general terms. But there are actually two basic forms of structural realism in the literature, and they're really quite different. First, there is epistemic structural realism. This is the view that the unobservable world has a nature beyond its structure, but that we can only know the structure. On this view, structural realism is an epistemological claim. It concerns the limits of our knowledge. We can build knowledge of structure, but the nature and the entities behind the structure will remain unknown. So this is about the limits of what we can know. We can only know the structure, although there is more than the structure. Second, there is ontic structural realism. When this treats structural realism as a metaphysical claim. The strongest form of ontic structural realism claims that there is nothing beyond structure. Science gives us knowledge only of structure because structure is all there is to the world. There are no entities, there are only structures. Obviously, this is an extremely bizarre kind of view. It's most prominently defended by James Ladyman and Don Ross in their book Everything Must Go. A weaker version of ontic structural realism allows that there are entities, but it holds that structure is in some sense primary. Entities are dependent for their existence and their identity on the structures of which they are a part. Entities are simply nodes within structures. And this contrasts with the usual view of entities. We would usually hold that an entity has certain intrinsic properties that it has in itself, regardless of its relation to other things. This weaker version of ontic structural realism holds that, okay, there are entities, there are objects in some sense, but these entities have no intrinsic properties. All of their properties are ultimately reducible to their place within a structure. Now, I should warn you that the literature on ontic structural realism is extremely technical. I'll do my best to introduce it, but I must say that a lot of this stuff goes over my head. I'm certainly no expert here, but I do have some idea of the basic kind of concepts, the basic arguments. So as I say, I'll do my best. But if you're interested, I recommend having a look yourself. But be warned, it's difficult stuff. Now, much of the motivation for ontic structural realism comes from quantum mechanics. James Ladyman has argued that there's a particular kind of underdetermination with respect to quantum mechanics that supports ontic structural realism. We've discussed underdetermination before. This is the claim that there are many different theories compatible with the same evidence. According to Ladyman, the worry about quantum mechanics is underdetermination with respect to the question of whether quantum particles are individuals. So, what is an individual? Well, we divide the world into individual objects, right? So what is it that makes, for instance, my computer a different individual from your computer? Presumably my computer is a different individual from your computer, but what is it that makes it a different individual? What is it that makes the Sun a different individual from Alpha Centauri? Well, an initial thought is that they're different individuals because they have different properties. They are distinguishable. In other words, we can specify differences between my computer and your computer. Even if they're built from exactly the same molecules in exactly the same way, we can specify differences in their spatial location. This leads to the principle of the identity of indiscernibles, which says that if X and Y share all the same properties, then X and Y are the same thing. So if X and Y are different individuals, there must be some difference in their properties. Are the objects postulated by quantum mechanics individuals or not? I'm going to simplify the science somewhat here in order to make the philosophical point. Consider two boxes, 1 and 2, and two particles, call them A and B. In classical mechanics, there are 4 possible states. We can have A and B in box 1, A and B in box 2, A in box 1 and B in box 2, A in box 2 and B in box 1. However, in quantum mechanics, there are only 3 states, because permutations do not produce new states. Right? There is no way to distinguish the permuted state from the original state. So there's no distinction between particle A in box 1 and particle B in box 2, and the state particle A in box 2 and particle B in box 1. Statistically, the chance of both in box 1, both in box 2, or that should say box 2 there, sorry about that. So we've got box 1, box 2. So statistically, the chance of having both particles in box 1 is a third, having both particles in box 2 is a third, having one in box 1 and one in box 2, that's a third. Right, those are the chances. Obviously, in the classical mechanics, the chance of having them both in box 1 is a quarter, and it's a quarter for all 4 states. Whereas in quantum mechanics, it's a third, because permutation in this case does not produce a new state. So what's bizarre about this is we can say that a particle is determinately in box 1 only if the other particle is also in box 1. But there's no fact of the matter which box a particle is in if each particle is in a different box. And that's not due to the limits of our knowledge. This appears to be a fact about the world. So there seems to be some sense here in which particles are indiscernible. They don't seem to operate like normal individuals. Let's consider another example. Again, this is something of a simplification. Suppose 2 particles collide. One is diverted upward by the collision and the other is diverted downward. Now, if we imagine a collision between everyday objects, such as billiard balls, we have 2 possibilities. Either the left is diverted upward and the right is diverted downward, or the right is diverted upward and the left is diverted downward. But for certain particles in quantum mechanics, there is no difference between these 2 situations. The most we can say is that 2 particles have collided. One's gone up, one's gone down. There's in the classical situation, there is a fact about whether the ball coming in from the left is the same as the ball that gets diverted upward. But for certain quantum particles, there is no such fact. I mean, an analogy here is, suppose that every day over the course of a week, I deposit £10 in my bank. Then on Sunday, I take out £10. Now, which £10 did I take out? Was it the £10 I deposited on Monday, or the £10 I deposited on Tuesday, and so on? Or was it some combination of the various deposits? I mean, obviously, there is no fact to the matter here. The most we can say is that I've deposited £10 over the course of a week, and then at the end of the week I take out £10. But there isn't a fact about which £10 that is. That would just be a mistake. That's a mistake about how bank accounts work. I mean, of course, there's. If you're depositing the money using physical money, if I have a collection of notes or coins, then there's a fact about which £10 note I use. But if we're talking about depositing money electronically, there is no fact. Anyway, these examples would seem to suggest that quantum particles are not proper individuals. Similarly, the electronic pounds in a bank are not proper individuals. And this is the assumption of most physicists. However, we can interpret things such that they are individuals. One way to do this would be to assume that quantum particles have a kind of primitive thisness. Identity cannot be reduced to sameness of properties. A particle's individuality is something over and above its properties. Basically, we could deny the principle of the identity of indiscernibles. Perhaps 2 completely indiscernible things, 2 things that share all their properties, are nevertheless not identical, because there is they have some special. There is a kind of primitive individuality that they have over and above their properties, and that makes them 2 different individuals. And I mean, there does seem to be some sense, after all, in which we have 2 particles in the quantum case. We have 2 particles colliding, one goes up and one goes down. So there are different things here. But the important point here is that the physics itself doesn't tell us whether or not quantum particles count as individuals. This is the underdetermination. This is not the standard underdetermination of theories by data. The point is that we can accept everything the theory says, and we still won't know the nature of quantum particles. So the scientific realist claims that our best theories of physics tell us the way the world is, or at least that our best theories of physics get it approximately right. But we can ask, well, what way is that? Are quantum particles individuals or are they non-individuals? These are radically different metaphysical views. Which of these views corresponds to the world? Our best science simply doesn't tell us, so there doesn't seem to be much room for realism there. Ladyman's solution to this problem is simply to dissolve it. The question of whether quantum particles are individuals or non-individuals, he thinks, is misconceived. Instead, we should hold that there just are no quantum objects. Quantum mechanics teaches us that the quantum world is nothing but structure. So, to put all of this together, Peter Ainsworth reconstructs Ladyman's argument as follows. Premise 1. If we take the ontology of quantum physics to be one of objects, properties and relations and so on, then the question of whether these objects are individuals or non-individuals is not resolved by the physics. Premise 2. If we take the ontology of quantum physics to be one of only relations, then there is no such underdetermination. Premise 3. If we can avoid underdetermination, then we should. Conclusion, we should take the ontology of quantum physics to be one of only relations. Since there are no quantum objects, the question of whether they're individuals or non-individuals doesn't arise. And of course, with this conclusion, we then note that the ontology of quantum mechanics is the ontology of the world. Ultimately, quantum mechanics is the fundamental science. As far as we know. Well, actually, there's string theory, isn't there? But certainly such sciences such as chemistry, biology, psychology and so on are all dependent on quantum mechanics in the sense that, as far as we know, everything in the universe is ultimately composed of quantum particles. If there are no real objects in quantum mechanics, then there are no real objects, period. Of course, on an everyday scale, talk of objects is very useful since it allows us to describe certain stable patterns in the structure. But the universe is fundamentally just structure. This structure does have stable patterns, and that's what allows us to talk about objects. But fundamentally, there aren't really any objects. It's all structure. Okay, I hope that was reasonably clear. I mean, in broad outline, I think the argument is relatively simple. What Ladyman's argument amounts to is the claim that there is an underdetermination in quantum physics with respect to the question of whether quantum objects are individuals or non-individuals, and Ladyman thinks that this underdetermination should lead us to reject the notion of quantum objects. We can avoid this whole problem if we just reject the idea that there are objects in quantum mechanics, and instead we should take it to be an ontology of structure. But I mean, as I said, it does get quite technical. But I hope that was reasonably clear. All right, let's consider a few objections. First of all, an obvious worry is that Ladyman forwards an underdetermination argument. But surely an underdetermination argument only has epistemological force. For example, our best theories relating to dinosaurs might be compatible with them having either grey feathers or black feathers. Our best theories of dinosaurs, in other words, underdetermine feather colour. Now, just because we can't determine what colours the feathers were, we wouldn't assume that therefore they had no colour, or therefore they had no feathers. Similarly, it seems bizarre to conclude that just because physics doesn't tell us whether quantum objects are individuals or non-individuals, therefore there are no quantum objects in its whole structure. In any case, it's not clear that Ladyman actually avoids the underdetermination. Notice that his theory that the ontology of quantum mechanics is one of structure, this is just one among many empirically equivalent interpretations. So Ladyman begins with the underdetermination that arises because quantum mechanics can't tell us whether quantum objects are individuals or non-individuals. Okay, but to say that there simply are no quantum objects, there are only structures, well, that just adds another theory that is compatible with the data. In other words, all Ladyman has done is shown that quantum mechanics is equally compatible with a third theory. So quantum mechanics, we could take it to claim that we could take the sort of metaphysical implications of quantum mechanics to mean that quantum objects are individuals, or we could take the metaphysical implications to mean that they are non-individuals, or we could take the metaphysical implications to mean that there are no quantum objects and it's all structure. So now the data underdetermines three theories. So it's not really clear that Ladyman has actually avoided the underdetermination problem by just giving another theory that is compatible with the data. A second rather obvious objection is that ontic structural realism is incoherent because there can be no relations without entities that instantiate those relations. Put simply, no relations without relator. Consider the relation heavier than. A is heavier than B. This seems to require the existence of the objects A and B. What would it even mean to say that the relation heavier than exists alone without there being any particular entity that's heavier than another? That doesn't seem to make any sense. The weak version of ontic structural realism might seem to avoid this problem because weak ontic structural realism does recognise entities, but remember that according to the weak ontic structural realist, these entities themselves derive from relations. So I think ultimately the objection stands in that case as well. So how might Ladyman and co respond? Well, notice that this is simply an appeal to intuition. Intuitively, all relations require relator. It's difficult for us to comprehend what it means to say that there could be relations without relator. But the problem is that quantum mechanics violates our intuitions in all kinds of respects. If you've ever read anything about the results that have been coming out of quantum mechanics, you'll see that it's incredibly bizarre. So we shouldn't be surprised or worried if the metaphysics implied by quantum mechanics also violates our intuitions. So Ladyman and Ross's book, Everything Must Go. The first chapter of that is a really brutal and, in my opinion, completely persuasive assault on the tendency of philosophers to appeal to intuitions. Philosophers will kind of say, that such and such is counterintuitive and so it can't be true, or the idea of there being relations without relator, well, that's incoherent, it can't be true. But Ladyman and Ross say, right, no, you can't just sort of sit on an armchair and appeal to intuitions. You've got to look at the science. The first chapter of that book is, I think, just a brilliant attack on the appeal to intuitions. So they would just reject this kind of appeal to intuition. A third objection is that ontic structural realism fails to capture the difference between mathematical or abstract structure and physical or concrete structure. There are many branches of mathematics which all describe many different structures. Consider the differences between Euclidean and non-Euclidean geometries. The point is that many mathematical structures are not true of the world. The world does not instantiate them. Or to put it another way, many mathematical structures are purely abstract. In contrast, the structures of the world are concrete and physical. There does seem to be a difference between abstract mathematics that doesn't apply to anything and the mathematics that describes the nature of the world. Now, the objection is that this difference can only be maintained if we postulate entities. If the structure is all there is, we can't distinguish between different kinds of structure. In response, Ladyman and Ross argue that actually there is no distinction between mathematical and physical structure, between abstract and concrete structure. Now, this, of course, gets pretty deep into issues in the philosophy of mathematics, but I'll note a couple of points. First, some philosophers of mathematics have argued that mathematical structures are literally part of the physical world. I have a video called Philosophy of Mathematics Platonism. If you go to the 54-minute mark in that video, I outline the views of Penelope Maddy, who has argued that mathematical structure just is physical. In particular, she thinks that there is a physical basis for set theory and that mathematics can be reduced to set theory. But again, go to 54 minutes in my video on Platonism for more about that. More importantly, Ladyman and Ross point out that when we try to define the distinction between abstract and concrete, we run into all sorts of problems. Now, there are many definitions of this distinction. I will mention the two that have been the most popular. First, many philosophers have suggested that something is concrete just in case it has causal powers, whereas something is abstract if it has no causal powers. The thought is that if you take a mathematical object, for instance, a number, let's say the number 17, the number 17 in itself doesn't have any causal effects on anything. Similarly for a triangle. Obviously, physical things in the shape of a triangle will have causal powers, but if you take a perfect mathematical triangle, the kind of ideal triangles that are discussed in geometry, well, that's not going to have any causes, it's not going to have any effects. If mathematical structures have any existence at all, they exist outside the causal web. Now, the main problem with using causality as a criterion is that it's not clear that causality has any role in fundamental physics either. There's been quite a long tradition of skepticism about causality deriving from considerations about physics. Again, that's technical stuff, but the basic point is that in fundamental physics, it's not really clear that causality has any place there. It arguably is something that sort of emerges when we look at the special sciences. So second, there's the suggestion that concrete things exist in space-time, whereas abstract things do not. Concrete things have a spatio-temporal existence. The number 17 does not have a spatial location, nor does it exist for any set amount of time. Now, the obvious problem with this definition is that space-time itself is studied in physics. So presumably space-time should count as concrete, but obviously space-time can hardly be said to exist in space-time. That wouldn't really make any sense. So basically, Ladyman and Ross think that we should just drop the distinction between abstract and concrete, which means there's no need for ontic structural realism to capture that distinction. Now, I'm not really convinced by this. I do agree with Ladyman and Ross that there are difficulties defining the distinction, but I don't think that means we should just junk it. It seems to me that there is a distinction between abstract and concrete, and this is entailed actually by physics itself. So we often use idealizations in physics. Physicists will talk, for instance, about ideal gases that perfectly obey the ideal gas law. We don't suppose that there literally are ideal gases. The concept is useful because under certain conditions, real gases will very closely approximate the behaviour of an ideal gas. But we all understand that the ideal gas is a concept that is never actually instantiated. The ideal gas law is never actually instantiated by a real gas, it's an abstraction. And there are numerous examples of abstraction in physics, frictionless planes, perfect black bodies, perturbation theory, infinitely deep liquids in the analysis of surface waves, the use of continuous functions to represent things like energy and charge, which we know are quantized. And of course we also appeal to theories that we know are strictly speaking false. For instance, we can use Newtonian mechanics in limited circumstances even though it's actually wrong. But the structure postulated by Newtonian mechanics is not the structure of the world. It closely approximates it in certain conditions, but it's not actually instantiated. So it seems to me that some sort of distinction between abstract and concrete is actually implicit in the sciences. Okay, one final thing that I'd like to note about ontic structural realism before we end. A primary benefit of ontic structural realism is that it is claimed to be a limited form of realism. It limits realism to structure alone and hence avoids the pessimistic induction by allowing theory change with respect to entities. But notice that, in fact, ontic structural realism simply accepts at face value what contemporary physics tells us about the nature of objects, namely that there are none. And in that respect, I think we could say that ontic structural realism is really just standard scientific realism combined with an unusual view about the nature of objects. If we have good reason to expect that views of objects change, then presumably we should also expect that what contemporary physics tells us about objects will also change. Even if we buy ontic structural realism for because of the arguments based on quantum mechanics and so on. It's not really clear that ontic structural realism can offer a response to the pessimistic induction, which is how structural realism, which is what structural realism was originally supposed to do. Of course, that doesn't necessarily mean that ontic structural realism is wrong. I just think it's interesting to note structural realism was originally conceived as a response to the pessimistic induction, but it's not really clear that ontic structural realism can do that. Okay, that's all. Thank you for watching.